Tyler here, who's from Princeton, grad student working with John Cohen, and he's going to be telling us all about adapting to changing environments. So I'm looking forward to this. Thank you.
Great, thank you. Yep. So as James mentioned, I'm going to be introducing a model for how humans might adapt to certain kinds of changes using their memories. This is collaborative work with Declan over in the corner and my advisor, John Cohen. So very broadly speaking, one really remarkable fact about human cognition is its flexibility. Humans are very good at performing a wide range of tasks, not very good at each of those tasks individually compared to the best AI for that kind of task or the best non-human animal for that kind of task, but probably the best at maximizing the area under the curve across all of these different tasks. And we can learn those new tasks very quickly in terms of the amount of data that it requires. And we can switch between all of those tasks within a single embodied agent. So I can go from building a dam, if that's something I knew how to do, to smelling something, to navigating, to playing chess, all within the same day without too much difficulty. And I want to focus on a few of those behaviors in particular during this talk, how we're able to adapt first to changes in the environment. So here we see Mario hitting this box. And what's interesting is that at first this box was a brick, and Mario would jump and hit the brick and get some coins. And after hitting the box a certain number of times, the shape of the brick changes into that sort of grayed out looking box, and there are no longer any coins. So basically the environment used to reward a certain kind of behavior in this situation, and now something's changed where the environment no longer rewards that behavior in this situation. Jumping no longer gives you a coin, and very little indicates this change except for a tiny visual change in the display, which is just that the color of the box has shifted. Another set of changes that humans are able to adapt to are changes in context. Context is a very squishy word that I'm going to not define later, but talk about how we might figure out what context is through learning in a neural network. So bear with me while I use it very squishily for most of this talk. At least two types of context are relevant towards a lot of kinds of changes in the environment. The first is internal context. So Mario is about to hit the star power up, which is going to make the gameplay very different. So when you have the star, you can run directly into the enemies, and that's kind of desired behavior. But without the star, you have to jump on their heads. So getting the star changes something about Mario's internal state that makes the relationship between the states in the environment, the actions that Mario is supposed to take, and the rewards that Mario achieves very different. There are also changes in the external context. So Mario might be underwater versus on land, and the way that the physics works underwater is very different. So the way that locomotion works is very different. So again, the associations between the states in the environment, such as if you're on the ground or not, the actions that you take, such as whether you jump or whether you go up or not, and the rewards that you get are going to be very different based on the external context, which here you can infer based on seeing like the wave pattern at the top of the screen, for example. So it's become a pretty popular explanation that these kinds of abilities, and in particular, the ability to adapt to new situations with a relatively small amount of data, relies on transferring knowledge across different situations. So in the old situation where you were getting that star power up, you might realize that standing underneath the box and jumping up to hit the bottom of the box gets some sort of I don't know, item that emerges from the box. And then you can transfer that knowledge to this new situation where the visual scene looks very different, but there's still a box and you can still jump. So you might infer that you should stand underneath the box and jump, and something good might come out of the box because that's what happened in this old situation. So this is potentially one of the reasons why humans are able to perform so many different tasks. We can take our knowledge learned in one context and apply that to another context. And this is not a new idea, and it's not a unique idea. We see it in cognitive psychology with the idea of things like schemas or analogical reasoning. We see it in machine learning with the idea of transfer learning or multitask learning or meta learning. And we see it in neuroscience and places that I forget, but I'm sure you can think of places in neuroscience where we imagine that transferring knowledge might be useful.
The example you just gave is a little bit like a macro.
Yeah, so it's yeah, exactly. So you can take some abstract information from one situation and apply it in a new situation. You're not in the exact same state, but you want to perform a very similar action to achieve a similar result. So it's about, yeah, taking knowledge from one situation and applying it to a new situation that's similar in some ways, but different in other superficial ways. Yeah.
So maybe you're gonna comment on this, but that's an insanely hard problem.
Yeah.
You don't really know what to move over. Tons of stuff constrained. Did you comment on that earlier?
Yeah, no, that's a really important point. I think the main point is you have a lot of experiences in the past. Some information from some of those experiences is going to be very useful and transferring to whatever the current situation is. Other information is going to not be helpful or even actively harmful. And that's one of the key trade-offs that an agent needs to make when generalizing. And that's a key point in the talk. Transfer knowledge, yeah. So I'm going to focus on episodic memory as a mechanism that might enable very data efficient transfer of knowledge. And a lot of recent work has focused on episodic memory in a kind of similar role, but this is a really weird perspective to take historically. So a lot of the early historical work on episodic memory involves presenting people with like a random list of words and then seeing how many of those words they recall and what factors influence their recall of those words. Here we're focusing on episodic memory as a means of enabling inference in new situations or action in new situations. So the way that that works is if you have a bunch of examples of playing Mario, like the classic version on the NES, that provides you a useful set of exemplars that you might be able to use when you're playing a new game, such as Mario on the Wii, that has a lot of similarities to the old game that you played. And you can infer maybe that from only a small number of examples of jumping on the heads of different animals in the old Mario game, that maybe that's a valuable strategy to apply in this new Mario game. And similarly, this other game also has this jumping mechanism, and you can apply your memories of Mario to this new game, even though the visual similarities are now quite different. You might still be able to use this motif of jumping on the heads of things in video games is a good idea. And obviously, that's not something that we do in nature very often. I can't remember the last time that I jumped for any purpose, and certainly not on the head of an animal. So that also highlights the remarkable flexibility of human cognition. After as few as one exposure, a single exposure to this idea of jumping on the head of something in one video game context, we can try applying that to a new video game context. Okay. However, as Peter was mentioning in the question earlier, it's a hard problem to know when to do that. So this other game is very similar in a lot of ways. It's still a video game. It has a knight in it, just like that other video game. But here in this video game, you don't want to jump on the heads of enemies. If you do that, I don't know, you lose points or something like that. So you don't always want to transfer from one situation to another situation. And the hard part is learning when do you want to transfer and what do you want to transfer. The main idea that we have about this is it's about context. So if you only access the context relevant memories, then you get the benefits of generalization, but you can limit the penalties of interference between memories. So imagine that you've grouped your memories into two different kinds of video game memories. Some where jumping is rewarded and others where jumping is penalized. If you do this, then you can, when you're in this new situation where Mario sees a spike ball, if you can somehow understand that this situation is similar to the knight situation where you shouldn't jump on the enemy, and maybe the Flappy Bird situation where jumping up is going to have you hit the object, and so that's a bad case where you shouldn't be jumping, rather than potentially the visually more similar other Mario examples where jumping is rewarded, then you're able to make the proper inference that you shouldn't jump. So it would be very useful for the episodic memory system in terms of enabling inference and behavior if it had some way of grouping memories based on what is useful for behavior. And so obviously this is a really hard problem and it's a really multidimensional one. As I already mentioned, and as is clear from looking at the display, in many ways, what determines the similarity of the memories should be that, you know, you're playing the same Mario game across two different memories. But for particular circumstances, for particular kinds of behavior, that should be reshaped to emphasize other kinds of similarities, such as whether jumping is rewarded or penalized. And I'm not going to promise that our model can deliver on quite this ambitious of a goal, but we'll focus on some more simplified cases where we see that this kind of grouping of memories can emerge in neural network architectures that are augmented with external memories. Okay, so to summarize, one of the ways that humans can rapidly learn new tasks with a small amount of data, which may explain our ability to perform such a broad range of tasks, is that we can use episodic memory to recall memories of encountering similar situations in the past and do now what we should have done in those situations, weighted by their similarity. So if I'm in a situation now and I need to know how I should act, I can think about memories of when I've been in similar situations and think what would have been the thing that I should have done in the past, and then just do that thing now. And that will help, provided that I have at least one memory of being in a similar situation in the past, and I know what I should have done in that situation. And the difficulty is I might have been in somewhat similar situations in the past that actually have the opposite rules or norms or customs that I shouldn't apply to this new situation. Okay. So we implemented these ideas in a neural network model that follows external memory neural network architectures. So if you're familiar with like the neural Turing machine or differentiable neural dictionaries, basically the idea is you take a fairly standard neural network, which is this thing over on the right, and you add an external memory to it. So the external memory is meant to be like episodic memory in that it stores individual exemplars of past experience. And it has three different fields. The middle field is the one that's kind of the novel contribution of this word. So those three fields are a representation of the stimulus, a representation of the context, and a representation of some kind of output that the system wants to associate with the input. So that might be the desired action, that might be the reward that was obtained in that situation, or it might be, if you're learning paired associates, the blue thing might be one of the associates and the green thing would be the other. So anytime the system wants to bind two pieces of information together that were experienced at the same time, it can add that episode to its memory by appending a new row to this matrix over on the left. So it's meant as a very simplified model of episodic memory, following this idea that episodic memory doesn't forget things, it just continues to accumulate experience, and it just becomes harder and harder to retrieve relevant memories as the list of experiences grows.
So what are green, red, and blue?
So the blue is a representation of the stimulus that comes from some embedding in a neural network layer. The red is a representation of context, which I'll get into how that works in a second. And the green is some other neural representation that should be associated with the stimulus. So and I think in all of the experiments I'm going to talk about, actually, so that's the reward.
Does each row go together?
Each row goes, yeah, so each row is one point in time. This is an outdated diagram, so my apologies for that. And these are three different pieces of information that basically get compositionally bound together because they were all experienced at one particular time step. So this 1, 2, 3.
So the green should tell you something about what the output should be given the input and the right?
Exactly.
Given the blue and the red, those match.
Then you get the green, you retrieve the green. Exactly. So using this kind of structure, the system can use the blue and the red now to see when did it have a similar blue and red at time steps in the past, and in those past time steps, what was the green, and then that gives you a prediction of what the green might be on this current time step.
Presumably that green works together with a network that combines similarity.
Exactly. So you can think that the green is like the output and the blue and red are like the inputs. And the blue is pretty straightforward. You just take whatever the stimulus is and run it through whatever a convolutional neural network if it's a visual input, or you just represent it as a one-hot encoding if it's some simple input. And the red is where things get a little more interesting. That's the context. So how does the system determine context? Really deep question that cuts across a bunch of different fields. As I mentioned, early work in episodic memory focused on this kind of like list recall type paradigms. And there you can think of context as kind of what led you to the current state. So it's something about the previous states that got you to the point you're at now. So one really famous example of an experiment in episodic memory is scuba divers were asked to memorize a list of words while underwater. And later they were put either on land or underwater and asked to recall those words. And they did a better job recalling the words learned underwater while they were underwater, not while they were on land, and vice versa for words learned on land. Those were easier to recall on land than in water. So this is the encoding specificity hypothesis. The idea there is that donning your scuba gear, putting the mask in, going underwater is a sequence of events that maybe all get encoded somewhere in the brain. And all of that kind of gets recurrently integrated over time through some recurrent network. And that sequence of events sets up a context. so that when you're learning these words, even though the words have nothing to do with being underwater, you have recently experienced a set of states that puts you in a particular situation where in the future you go through that set of steps again, you're underwater again. That sets up a red context that helps you recall the last time you were underwater, and that's where you retrieve the words. So in the simplest form, context is just what you experienced immediately before the current state. In more complicated situations, like with those video games, this sort of simple linear integration of past experiences is not going to be sufficient.
So
Yeah.
I must miss something, because that definition, what's the difference between the context and the embedding?
So the embedding is what you're currently experiencing. So it's the list of words that you're trying to memorize, or each word individually in that list would be a different embedding. The context is some sort of temporally smooth average of what you've seen before. So this line is the key distinction. This is a recurrent network, whereas this is not. So because this is in a neural network architecture, you can also just learn some nonlinear mapping between the embedding and the context. So maybe what that nonlinear mapping looks like is it focuses on the background in the Mario game rather than on the object specifically.
Instantaneous nonlinear versus recurrent?
Yeah, so this is this is just some projection layer. So you can take whatever the embedding is and pass it through like a standard feed forward set of weights, and then that is the thing that you can recurrently integrate into context. Or you can make context some more complicated like LSTM and let the weights in the LSTM be learnable and receive the embedding as a. So it depends on how complicated of a task space you're modeling, and we do a couple of different experiments that use different versions of context. But the idea is some sort of, you can think of it as maybe like a frontal area that is connecting to a lot of different, modality-specific regions, takes in all of this information, makes a decision about what to store in working memory. So that red thing can be thought of as working memory. And then you dump your contents of working memory into your episodic memory alongside whatever the current stimulus is. And then in the future, now you can use your working memory to recall particular examples from your past experience. Yeah.
Yeah, so in that example of Mario, right, embedding with information on the background, but actually the context dependent information that it's sort of gated, and probably no longer.
Yeah, so the context information can gate into working memory, whatever might be useful for the current situation. So if it arises through learning, it depends on what the training objective is. It might be that you have the power up. So when you get that star power up, that will be part of your embedding. And if you've learned the right weights into working memory, then you can store in working memory, I'm in the invincibility mode because I got the power up, and then that can affect your behavior. Yeah. Does that answer the question?
Yeah. I mean, it's just in terms of like foregrounding background information of life, right? Like Mario is a really kind of disjoint example where basically the background information does nothing after it's running context. But it can be very helpful.
Yeah, that's right. I think backgrounds are interesting because they don't change as frequently over time. So if I'm integrating something into working memory, this room has been stable for a long period of time. So that's probably going to get reflected in the red a little bit. Whereas the location of individual people in the room might be changing, other aspects might be changing. So yeah, it's not always useful to store the background in working memory, but sometimes it is. Okay, so we tested 2 experiments. We simulated 2 experiments using this framework. Both of these experiments exist in the literature and had very different models that the experimenters used to try to explain human behavior in these situations. And so we unify these accounts with this episodic numbering model. So the first experiment is this reinforcement learning paradigm where participants see a sequence of states, and at the end of the sequence, the last state is associated with reward, and the environment changes in one of 2 ways. Either the reward associated with the state changes, so 5 used to be worth $1, now it's worth 10, or the transitions between states change. 3 used to lead to 5, now 3 leads to 6. And at the end of the test phase, participants are asked about these initial states that lead to the intermediate states, but were not experienced during the revaluation phase. And this is a key manipulation because it prevents model-free reinforcement learning systems from learning anything, because the model-free system only experiences 1 in the first case, never in the second case. It has no idea that something has changed. Whereas model-based reinforcement learning systems that keep track of the transitions between states and that keep track of the rewards associated with each state are able to handle both kinds of transitions just fine. So that was the original manipulation, this model-free versus model-based kind of distinction. The interesting result is that humans don't act fully like the model-based system. they don't fully learn how to update their behavior following the change in the environment. So first of all, if they fully updated their behavior, these bars would be at 1 and they're closer to 0.5. So humans are kind of halfway between changing their preferences when the environment changes and not changing the preferences at all.
So random would be 0?
So yeah, 0 would be you have no change. So 0 would be that at first you prefer state 2 because it leads to $10. You learn that the downstream consequence of 2 changes and you don't care, you switch to 2. That would be 0. The second, yeah, oh, 5 minutes, okay. The second weird phenomena is that people are more likely to revalue, to change their opinion when the rewards change rather than when the transitions change. It's easier for people to handle the case where 5 used to be worth $1 and now it's worth 10, than it is to handle the case where 3 leads to 5, but now 3 leads to 6. And basically, in the interest of time, I'll skip through a little bit. Okay, I won't skip through that much. Basically, because the context is integrating over time, it has this like recurrent nature to it. We can explain why humans have the difference in these conditions in terms of memory. So in terms of our memory model. So basically what happens is the model updates its context in this recurrent way. So it's sort of storing the trajectory of the states that led up to where it currently is. And then when it needs to evaluate how good is state 1, it can replay its memories and it can go back in time to its memories and say, what happened the last time I was in state 1? And it sees that the last time I was in state 1, it led to state 3. And then it says, okay, it was in state 3. Let me query my memory with state 3. What happened the last time I was in state 3? I got no reward and it led to state 5. And so it replays through its sequence of memories to try to anticipate what the value of the current, what the value of the state is in the current context. And essentially what happens is because of this bias in memory, and these colors are probably going to be impossible to see. Basically what happens is the context representations learn a map of where you came from. So when you're in state 3, the context says that it came from state 1. When you're in state 5, the context says that it came from state 3, and before that, it came from state 1. And when the rewards change in the second phase, even though 1 was never seen, again, directly associated with 3 and 5, because the model is retrieving its memories, it can kind of remember that, and this is where you can't really see, they can kind of remember that state 5 came from state 3, and before that, state 5 came from state 1. But when the transitions change, it becomes harder to remember that state 5 used to come from state 1 because state 3 no longer leads to state 5. So there's basically this conflict in memory. Yeah.
So the question is, if you train this model on different stations and tasks like that, or it's just a single task like that?
So the model was trained on a task like this that humans also were trained on.
Like a single one that's fishing like this, where you train on lots of different like meta-learning tasks like that.
So that's an interesting question. The model isn't actually trained to do anything. Here, all that the context does is it just integrates over time. So it sees state 1. There's no learning in this case. So the way that it can keep track of where it came from is just because you see state 1, you gave that into working memory. You see state 2, you add that to working memory, and there's a little bit of decay. You see state 3, you add that to working memory, there's a little bit of decay. So it just sort of naturally keeps track of where it came from. Yeah.
So in the case of reward revaluation, why does anything change? Everything's exactly the same except reward. Why the context shouldn't the context stay exactly the same?
Yeah, so what the context allows you to do is it allows you to go back into your memories and see that state 1 leads to state 5, which is really huh?
It's just worth a different amount of time.
Yeah, exactly. So people do well at reward revaluation because state 1 still leads to state 5.
Why is the learned context changing at all?
Oh, the context changes because you experience a bunch of trials of 3, 5, 3, 5, 3, 5.
Oh,
so 1 isn't there anymore.
Yeah.
Yeah. But it still remembers from its past experience that 1 can lead to 3, lead to 5. Yeah. Okay. So basically, the model has this model-based reinforcement learning-esque ability of going back in time and sequentially sampling its memories. But it also has this successor representation-like feature of keeping track in its context of where states came from. And if you don't know what the successor representation is, it's not that important. It's just an alternative strategy for reinforcement learning. So combining those two features of this context and this iterative recall of memories, the model can show this adaptation to change in the environment. I will very quickly jump to the punchline of the next experiment. So basically, what's the problem here? The problem is that your old memories from the first phase of the experiment interfere with your new memories when things have changed. So it's like Mario interfering with Flappy Bird. Why would the system be designed like this? Why bother keeping around old memories when things get completely updated? The answer is you might go back to playing Mario in the future. So you don't want to forget about Mario. Even though Mario messes you up when you play Flappy Bird, maybe you're going to play Mario later, so you want to keep those memories around. So we investigated this kind of phenomenon in this task, where basically the people had to learn two tasks that were entirely contradictory. In task 1, you see something like state 1 leads to state 3. In task 2, you see something like state 1 leads to state 4. And participants experience them in this kind of blocked way where they do a bunch of task 1, and then a bunch of task 2, and then a bunch of task 1, and a bunch of task 2, or interleaved, where they just kind of randomly go back and forth between these two tasks. The behavioral finding is that this version, where you do a bunch of task 1, a bunch of task 2, a bunch of task 1, a bunch of task 2, works a lot better. So if you play Mario and then Flappy Bird for like an hour each or something, you do a lot better than if you're constantly jumping back and forth between Mario and Flappy Bird. This is weird because neural networks are the opposite, right? Neural networks like interleave training, they have catastrophic forgetting when you block things. Why might this be? And our answer to that was memory effects. Basically, you get a nice coherent context when you play a bunch of Mario in a row that lets you learn a coherent context representation for playing Mario, and then you play a bunch of Flappy Bird all in a row, and then same thing, you get a nice Flappy Bird context representation. So yeah, the main behavioral effects of people do better in blocks. Humans do better in blocks, they're close to 100% accuracy, then in interleaved where they're close to chance. The model has the same effect. It does much better in blocks than it does in interleaved, whereas a standard neural network, as I mentioned, has the exact opposite situation where it cannot learn at all in blocked, it catastrophically forgets, but in interleaved it does fantastic because neural networks like interleaved things. So takeaway point here is that memory effects mean that having temporally consistent experiences helps you learn a coherent context that might help you retrieve those memories in the future, which might explain why humans are better at blocked learning than interleaved learning in certain cases, even though neural networks are different. Yeah, okay, that's the main point. So the summary is that you can adapt to reward revaluation and transition revaluation. You can learn how to extract these contexts of playing one game versus playing another, for example, even though the games contradict with each other. And you can do all of that showing the same biases that humans do, which is that they learn one type of change in the environment better than the other, and they learn better in block than interleaved. All by integrating episodic memory into this kind of reinforcement learning framework. So that is it.
Brilliant, thank you very much. Open the floor for any questions.
Fantastic talk. I really like one thing I was wondering, maybe this is exceptions to the model, or maybe it's going to be an average, but so the extent to which episodic memory builds really depends on how the memory is. So if you have this example of 2 games, so Mario you train this system over time on just those 2 games.
Yeah.
It will learn to represent ways that are useful to that.
Yeah.
People can right? Like suppose I put those blocks of Mario, those represent my Mario in ways useful. But then you can see the third game where Mario memory is useful, so I think it's level of abstraction or like some very different way. It feels like probably do that. Like reassess the structure of the memory. It doesn't do this. Could you model that?
A little bit, yeah. So one of the benefits of structuring the model in this neural networking way is that the context representations it learns are high dimensional and distributed. So context is not this very simple binary flag of am I in Mario versus am I in Flappy Bird, which allows it in more complicated situations to learn some nuanced ways of representing things. Like maybe instead of just saying I'm in the Mario context, the context representation, since it's high dimensional, can say things like I'm playing a game where jumping is valuable. I'm playing a game that involves an Italian plumber. All sorts of useful contextual information at different levels of abstraction that some of those pieces might be useful for a new game. Some of those pieces might not be useful for a new game. And so what happens is if you look at the context representations that develop, And in this diagram, it's only for the 2 games, so it doesn't get at the rich kinds of cases that you're talking about. What you see is that the similarity structure of the context is coherent within the game and different across the games, because here the games don't help each other. But if you introduce a 3rd game that maybe you have like game 1 and game 2 very similar, game 3 not that similar, the context representations kind of reflect this gradient of similarity, where game 1 and game 2 will share overlapping context distributions that in context space are very similar to each other, whereas game 3 will have one that's a bit further away. But yeah, that's a really interesting question that needs a lot more work to answer fully.
I like that.
Any other questions? Yeah. So what you've got a sort of episodic memory system where you effectively have some sort of contextual gating of memory.
Exactly.
That contrasts to the classic Cohen model where you still this sort of gating of representation, but it's not happening by and then I'm presuming that's useful because all the time you see things that's like very blocked stance, so that sometimes you see something and then like a year later you see something. So, like I wonder how we all interact with each other.
Yeah, that's a good question. So work that we've done that wasn't included in this talk is looking at the interaction between those kinds of pathways. So if you have a semantic pathway that's a little more fleshed out, then what you might have is some context-dependent layer in a neural network, for example, that receives input both from the environment directly and from context, like from working memory. So it's sort of a semantic memory analog to the episodic memory side of things, where over time, when you consolidate information, you might be able to, instead of querying examples of individual memories in the past where you played Mario, you might have developed a summary representation in semantic memory of across your many years of Mario playing that extracts more general structure. And so what we find is that using a single context representation, so one PFC, you can coordinate both processes. So you can use your context representation to retrieve only memories that are context relevant. And you can use that context representation to bias processing in your semantic pathway. So for example, maybe it does like feature-based attention or something like that. So the representation in PFC will say something like, what dimension should you be paying attention to? And that will help you perform the task by biasing processing in the semantic pathway. And it can help you retrieve memories of when you've been doing a similar task in the past. Yeah.